I think if you send it to somebody that that runs the YouTube channel, they can post it there.
Yeah. Okay. Okay, so have you guys gone over the Unit 2 review on your workbooks? On page 175. Yes, some people say yes, some people say no. Okay, for the most part it's no, which is good, because then that means that it should be new to you. But if you already have done it, well then you're already ahead of the game. That's good. Okay, so then in that case, we'll go ahead and go off of the Unit 2 review. Okay, let me see. Okay, so then we'll just go in order. We'll have you do, let's try 1 through 3 for now. Module 7, no, Module 7 isn't going to be on your exam. The review is on page 175 of your workbook. 175, it says Unit 2 review at the top. Okay. So in the meantime, because I know like we all tend to work kind of like at different paces, we'll give you a bit of time to work on the first 3. And then in the meantime, you can either ask questions, turn on your mic, and go ahead and ask so we can all help each other out. And then after a couple of minutes, we'll regroup and then we'll work them out together on the board.
The Peerleader YouTube channel, I'll put it in the chat. Give me just 1 second. Let me get the link for you guys.
I don't know Zoom at all.
I do have it. Oh.
How do I do the whiteboard thingy? I forget.
Okay. If you go to share at the bottom, it says whiteboard.
Yeah.
Cool. All right. T. Okay. So then for now,
Okay, good.
okay. Blackboard. There you go. Sophia's linking you up.
Oh, yeah, the link I put down there that's the YouTube channel for the Peerleaders. Great.
Okay, so for now, 1 through 3 on your Unit 2 review. Oh, I didn't mean to write that. You guys can write on it at the same time too, right? Sophia and Maddie?
Yeah.
Yeah.
It's so like weird being able to like do this virtually, I think, because I'm used to the whole bunch of noise for the review sessions in person.
Yes, yeah. We're doing a Unit 2 review, page 175. I'm sorry, yeah, 75.
Yeah. So for now, try to like figure it out on your own, and then you can ask questions in the meantime if you get stuck, and then we'll go ahead and what will we be able to use during the exam? It's the same thing as your other exams. You know, a non-programmable calculator, scratch paper, I think. Yeah, I'm pretty sure scratch paper, something to write with. And how's Noveron doing it with you guys for the periodic table? I don't think he mentioned.
I think he said they could have one. Last time they could have their own.
Just as long as you like show it to your Respondus recording before you start.
What do you mean by cheat sheet? Like formulas or?
Like have the table of which one's soluble and insoluble, along with like examples, so that we can have a good idea of what's soluble or insoluble.
He didn't mention that to us. So right now we're kind of like trying to play it safe by saying no. So then the best advice we could give you is just like try to know your solubility rules and stuff like that.
And
So
we can ask him tomorrow, like right at preview.
Yeah, we can ask him on Friday and then let you guys know, or like we'll have your peer leaders tell you. But as of right now, we don't think you can. So even though, like, just in case, just try to memorize your solubility rules using the mnemonics, like Cash and Gia and Kakops and all that stuff.
Okay, so let's start with number 1, guys. So it's saying what neurotransmitter has the largest percent by mass of carbon, and then oh my god, how do I annotate? Okay, cool. And then it gives you adrenaline, which is C9, H13, NO3, then C8, H11, NO3, and then dopamine, CH, NO2, and finally it gives you C10, H12, and 2. Oh, okay, so any ideas, guys, which one is going to have the largest percent by mass of carbon?
What do they
based on what you're looking for? What's that?
I think what do they mean by percent by mass?
Because the carbon is higher.
In which one? I'm sorry, Aaliyah?
B,
In B?
the last one.
The last one, right? Because you have like 10 carbon, right?
Yes.
Okay, so that's right. Okay. And then I don't know if Maddie, do you want to do number 2?
Yeah.
Okay, cool.
Number 2 is which of the following does not have the same empirical formula? So it gives you some drawings here. You have 2 carbons and they're triple bonded to each other. That's your first drawing. This one's your second one. And then, let me see. Yes, the review's being recorded. You guys can all see the pictures, right? Yes. Okay, do you guys have any ideas, like, while I continue drawing this, because it might take a while?
Yes, it's the second one because it has 5 carbons, so the other ones are all multiples of 2.
Right.
Okay, yes, that's right.
So then pretty much what you would do, just so we're not like spitting out answers out there. So then you would try to like look at every single picture individually and then try to write a formula out of just what you see. So then, for example, if I have, let me use a different color. This first one right here, answer choice A. And if I just want to write a formula based on what I'm solely being given, how would I write this as a molecular compound?
Would that be H2C2?
Yeah, most of the time we'll write the carbon first, but yeah, potato, right? It's just like flipped. So yeah, C2H2. So then first what you would want to do is write the molecular formulas for all your answer choices, and then also write the empiricals and find the odd one out, right? So then if we look at answer choice B, what would my molecular formula be for this one? If I count my carbons and my hydrogens, there we go. In the chat, we have C5H6. Okay, and then answer choice C. How can I write this as a molecular formula?
So someone saying C6H6.
C6. Okay, in the meantime, while Maddie finishes drawing out this one, let's go back to A and find the empirical formula of it. So this is my molecular, because remember, the molecular is the one that's the longest one. Empirical is when you simplify it down. So then if I want my empirical formula for this, what is it going to look like after I simplify it down? Just
exactly. CH, real, yeah.
CH, right? And then can I simplify this one right here for B? No, right? Because of my 5, that kind of like stumps me. I can't simplify it further. Okay, so then now for answer choice C, I have my molecular, and what does my empirical look like for that one? CH, right? Okay, and then now for D, what's my molecular formula for this one?
So Joe is saying CaH8.
And then my empirical, CH, right? Just like the other ones. So now from here, you would look at all your empiricals and you would find that answer choice B doesn't have that CH, so then you would pick that one. It's your odd one out. Okay. Easy peasy for now, right? Alrighty. Okay, so we're gonna go ahead and clear this out. So if you got a nice cute picture of it, alrighty. Okay, so now we're moving on to number 3. Number 3 says ethane, which is C2H6, reacts with oxygen gas and creates carbon dioxide gas and liquid water. If 2.5 milliliters of water was produced, how much ethane gas was combusted? So we have a lot of stuff going on here, right? So let's try to dissect it and try to write down what we do know. So we're starting off with ethane. They already give you the formula for it. So luckily in this problem, you didn't have to have it memorized. And they're saying that it's reacting with oxygen gas. So how do I write oxygen gas as a formula? O2, right? How come it's not just O? Why do I have to have that 2 in there? Right,
yeah,
because it's a diatomic element. All my diatomics should have 2 afterwards when it's in its elemental state. Okay, so then it's reacting and it creates carbon dioxide gas, and liquid water. So how do I write carbon dioxide as a product? CO2, and then of course water. Just in case someone out there doesn't know. There you go, H2O, beautiful. Okay, so I have a nice reaction going on. But before I get started with any of the numbers, what do I have to do to this equation? Balance it. Right? So I have to make sure that everything is in order. I have my coefficients in there. So then what numbers, what superscripts, coefficients should I add in here? How did you all balance it?
You can speak up, guys. Like, you don't have to just write in the chat.
Yeah, don't be scared. We're all friends here.
Yeah. Come on, Joe, speak up.
We don't bite, we promise.
1, 1, 2, 3. Well, close. Not exactly, because if we do that, look, I'm gonna do it in a different color. I have 1, 1, 2, 3. That would give me 2 carbon, 6 hydrogen, 2 oxygens, and then on my right, I have 2 carbons, 6 hydrogens, but then that would give me 4, 3, 7 oxygens. So then something's off.
I think it would be 1, 5, 2, 3.
Okay, so then if we do 1, 5, 2, 3, yeah. I like this eraser, it's fast. Not like Blackboard. Okay, wait, how do I, okay. Well, if we have 1, okay. Okay, 1, 5, 2, 3. That would give me 2 carbons, 6 hydrogens, 10 oxygens, 2 carbons, 6 hydrogens, and then this is 4 oxygens here, and then 3 here, so then that would be 7 oxygens. So something's still a little off. So then we're gonna go ahead and try Sophia's, and she's suggesting 2, 7, 4, 6. Oh no, I deleted half my ethane. Okay, hang on. C2, there we go. Ah. There we go, thank you. Okay, so we have 2, 7, 4, and 6, which should give us 4 carbons and 12 hydrogens, 14 oxygens on this side, and then 4 carbons, 12 hydrogens, and then 8 plus 6, 14 oxygens. So when you're balancing your equations, be really careful if you have oxygens in like 2 different compounds. Make sure you're counting both so your balancing isn't off. But okay, I still love that you're participating, so keep that up. Okay, so now my equation is beautifully balanced. So now I can start working with my numbers. So for right now, I'm just gonna write down what I know. So then they're telling me that I have 2.5 milliliters of water. So I'm gonna write that here below. 2.5 milliliters, and we want to know how much ethane was combusted. So then we don't know ethane, and they're gonna want us to find out in liters because all my answer choices are in liters. And they also give me that extra piece of information saying that my density of ethane, C2H6, is going to equal 0.00124 grams per milliliter. Super important. It looks like it's a useless piece of information, but I promise you that it's going to come in handy. Okay, so now from here, it might look a little bit scary. We're working with milliliters. You're like, I don't know what the heck to do with these milliliters. But then if they're giving you the hints for ethane that you're gonna have to work with density, so then how can I convert my milliliters of water to grams? Because that's what density is for. So I can convert milliliters to grams.
It's in grams and milliliters. You could try to convert the grams into moles.
Yeah, so then milliliters to grams and then grams.
Molarity.
Well, we can't exactly do molarity because they're not giving you a concentration. They're not giving you anything that has a big M on it. So then right now we're gonna stick to density. So then what do we know about the density of water? Right here on the side. Density of H2O. Not milligram. You're on the right path. I can see your train of thought, but not exactly milligram. There you go. So it's going to be 1 gram per milliliter, which is the same thing as 1 gram equals 1 milliliter. So then this tells me that when I convert these 2.5 milliliters of water, what are they going to become? 2.5 grams, right? So I can just literally scratch this out and write a G instead. Okay, so now that I'm in grams of water, does it look a little bit less of a load? Now what can I do with these 2.5 grams of water? Grams of H2O. Someone mentioned it earlier, and you were right. You were just a little step ahead. You convert to moles, right? So then I convert to moles. I'm gonna have grams at the bottom, mole, 1 mole at the top, and what's my molecular mass of water?
1.008.
1.008 just for the hydrogen alone. But for my H2O altogether, I'm looking for 18.
Oh, my fault.
There we go. Love the spirit. Okay.
Yes.
So
Me
then
too.
from here, again, I'm just putting grams at the bottom so I can cancel out grams and grams. And so I can be left with moles once I get my moles. So then how many moles of water do I get after I convert? About 0.139, and it should be moles of water. Okay, so then now I'm at moles of water. So now can I use this to convert to ethane? And how do I do it? Okay, so I'm getting divide by 6, multiply by 2. So yeah, I want to use my balanced equation, and I'm going to pull my mole ratio from that. So then my balanced equation tells me that for every 6 moles of water, I can make 2 moles of ethane. So I'm going to use this to convert from moles of water to moles of ethane. So then I'm going to go ahead and put 6 H2O at the bottom, so I can cancel out H2 and H2O, and then 2 ethanes at the top. There we go. So I can cancel out my water and I'll be left with moles of ethane. So then after I use my mole ratio, how many moles of ethane do I end up with?
Is it 0.231? Multiplied by 2. My
There we
fault.
go. Make sure you're doing both the times 2 and also the divided by 6.
Okay, so would it be 0.463?
Yeah, so we should get 0.046. We'll just cut it off right there, you know, to not make our lives harder by going the extra mile. Okay, so then that's moles of C2H6. Okay, but they're not looking for moles, right? They're looking for liters. So then what's the next step I should take with these moles? I'm at 0.046 moles of C2H6.
Multiply it by the milliliters of C2H6.
Okay, so then what we're going to do is we're going to find grams by using our molar mass, right? So then obviously you have to calculate your molar mass. And after you do that, what do you get for me to plug in here to my grams per mole?
30.1.
Yeah, 30.1, right? There we go. 30.1, and then you multiply times your grams, well, times your moles of ethane, and how many grams do you end up with? About 1.38, right? So we'll do 1.38. We'll cut it off at 4, but round up to 5. Okay. And then from here, we're at grams of ethane. But again, they don't want it in grams. So now what's my, not last step, but second to last step? This is where my density guy is going to come in. So see, he wasn't entirely useless. He was just sitting there watching, but now he's going to come into play. Okay, so then we want to find milliliters and then convert that to liters, right? So I'm going to go ahead and just do a longer fence just so we can get this over with. And I'm going to put my density at the bottom, 0.00124 grams per 1 milliliter. And then what's my conversion factor for milliliters to liters? 1 liter is equal to how many milliliters? 1,000, right? Oh, I had it backwards. Oopsies, hang on. Okay, 1 liter and then 1,000 milliliters. So then go ahead and plug this into your calculator and let me know what your final answer is.
1.12.
1.12, right? 1.12 liters. So then that makes it answer choice A. So I'm going to pick A for that one. Do you have any questions on this question? No? Alrighty. So if you don't have any questions, we're gonna go ahead and move on to the next bit. Okay, do you guys like want to try to figure it out by yourselves and then like we come in and work it out together? Or do you just want us to go straight for it and just go in order? Like no stopping. No stopping, alrighty. We love that spirit. Okay, cool. Alrighty, so now Sophia's gonna take over for this next one. Go ahead and share the screen.
Okay. So can I clear this, guys? Okay, yeah, it's cleared, never mind. Okay. Okay, so for this one, it's saying to use the following equation for the next two questions, and then the equation is, so it's 2 magnesium solid plus carbon dioxide solid, and then 2 magnesium oxide solid and carbon solid again. Okay, so the question says, a sample of 5 grams of solid magnesium were deposited inside a block of dry ice and completely reacted. How much carbon was produced? So what do I start with, guys? Any ideas? I can't read the chat box, so if you don't mind speaking up, that would be awesome.
We start with like the grams of magnesium.
Yes, okay, exactly. So I have 5 grams of magnesium, right? Okay, and we need to get, it's asking me how much carbon is produced, right? So I want to get to carbon grams, right? Okay, this is what I don't know. Okay, so I would do a dimensional analysis for this. And so I have grams, so what do I have to convert my grams into?
Do you go to moles?
Yes, exactly. Okay, so check your periodic table. So per 1 mole of magnesium, how many grams are there?
24.3 grams.
Yes, okay, so 24.3 grams of magnesium. Okay, perfect. Okay, so now you want to know how much carbon you're producing, right? So refer back to your equation and see how many moles of magnesium and carbon there are. So what would go here, guys? What would go up and down?
2
Two.
moles of magnesium.
Yeah, so would that be on top or on the bottom?
On the bottom.
On the bottom, right? Okay, so 2 moles of magnesium, and then we'll go on top, guys.
1 mole carbon.
Yes, okay, perfect. So 1 mole of carbon. Okay, so what do I need now? So it's asking me how much carbon was produced, right, in grams. So and down here, any ideas?
1 mole of carbon in the bottom.
Yes, because yeah, exactly. 1 mole of carbon.
And then Avogadro's number on the top.
On top. So first I need to find my grams. So
You
so
put
you
the mass of carbon on
Yeah.
the top.
So
yeah, exactly. I need the mass of carbon, right? And what is the mass for carbon, guys?
12.01.
12.01, you said?
Yes.
Yes, grams. Okay, perfect. Okay, so now what you plug this into your calculator, and what does that give you, guys?
1.23.
1.23 grams of carbon. So your answer is that 1.23 grams of carbon are produced, right? When using 5 grams of solid magnesium. Now, you know how right now someone said about Avogadro's number? So look at question number 5, and what is it asking you for?
For atoms.
Atoms.
Exactly, atoms, right? Okay, so referring back, I'm gonna okay, I don't want to delete it, but okay, I'm just gonna write it real fast. Wait, okay, so how would you get from where we are right now? Like, pretend we stopped like right here, right? So like this is what we use to find our grams. But what would we have to do if we wanted to find our atoms? Per 1 mole of carbon, what would go up here, guys?
Avogadro's number.
Avogadro's number, right? Okay, and what's Avogadro's number?
6.02 times 10 to the 23, I think.
Yes, times 10 to the 23rd. And then remember to specify, right, carbon atoms. Okay, and so you would plug all of this in, guys, plus the, like, times the 6.02 times 10 to the 23rd, and what would this give you?
(1.24 times 10 to the 23rd).
10.24, okay. Did anyone get something else?
Are you asking for like the final answer? Or
Yes, so you get, okay, so remember right now, so we did 5 grams of magnesium. That's what you're starting with. And then you know that 1 mole of magnesium is 24.3 grams of magnesium. And you know, looking back at your equation, that when you have 2 moles of magnesium, you have 1 mole of carbon, right? So this is pretty much the same. But then now it's asking you to find the carbon atoms. So instead of converting to grams, you would have to find the carbon atoms, right? And the way you do this is that per 1 mole of carbon, there's 6.02 times 10 to the 23rd carbon atoms. Does that make sense? So this is how you would find it. So you would have to plug like all of this into your calculator.
For the answer, I got 6.19 times e to the 22nd.
Times 10 to the 22nd?
Yes.
And then carbon atoms, right? Okay.
Yeah.
Did everyone
It's just
get
on the other page, isn't it?
Yeah, it's on page 176. Like, it continues there. It gives you like more options. Okay. Any questions on this? No? Okay, cool. So let's move on, guys. Maddie, do you want to do number 6?
Yeah.
Okay, cool.
Okay. So number 6, it's saying hydrogen and nitrogen react to form ammonia. But even if there are coefficients, you always want to just double check and make sure because there could be a mistake. So it's saying we have 4 moles of hydrogen gas and 2 moles of nitrogen. So what would be our first step here, guys? Because it's asking for our limiting reagent. What's our first step in this problem?
Anyone?
The moles of hydrogen.
Yeah, the moles of hydrogen. Okay, so if we have our moles of hydrogen, we're gonna be using dimensional analysis for this problem. So what's like the next part of our fence here?
3 mole of hydrogen in the bottom.
Grams. Wait, no. What she said.
Yeah, it's 3 moles of hydrogen on the bottom. So then what are we gonna have on top?
1 mole of nitrogen.
2 moles of ammonium.
Oh, yeah.
Yeah, it's actually going to be 2 moles of ammonia because you want to find out like, you want to find out how much ammonia is forming, how many moles of ammonia. So we have 2 moles of ammonia. Okay, so then if we plug this into our calculator, what does that give us?
2.67.
2.67 moles of ammonia. So then we're just going to follow the same process, but we're going to use nitrogen. So then what's the next part of my fence?
1 mole of nitrogen in the bottom and 2 mole of ammonia in the top.
Yes. So if we plug that into our calculator, what do we get?
4.
Yes, we get 4 moles of ammonia. So then if we look at this, we can determine our limiting reagent. So you guys want to take a guess which one of our reactants is going to be our limiting reagent?
Hydrogen.
Yeah, it's going to be hydrogen. Do you know why?
Because it's the smallest.
Yeah. So whenever you want to find your limiting reagent, you want to find out which one of your reactants produces the smallest number of your product. In this case, 2.67 is obviously smaller than 4. So hydrogen is going to be your limiting reagent here. Are you guys all good on that one?
Yes.
Okay. Brittany, I don't know if you want to do number 7.
Yeah, I'll go ahead and do it.
Okay.
Okay, we're gonna go ahead and clear this out. Okay, number 7 looks a little wonky. I know that even my first time doing it, I was a little like, oh no, what the heck am I looking at? But okay, once you break it down, hopefully you realize that you do know everything that they're asking you for. You just kind of have to like piece the information you already know together to try to find your final answer. So then for this one, they're saying in an attempt to isolate solid iodine, potassium iodide and aqueous chlorine are reacted. A salt is a byproduct of this reaction. If a total of 25.38 grams of iodine solid was collected, how many electrons were transferred in this reaction? So there's a lot going on, right? They're telling you, okay, you're using these elements to form this. I'm giving you an amount of iodine that you're starting with, but we also want you to know the electrons transferred. So then first let's go ahead and, like every other problem, try to write an equation out of it. So then if we're starting off with iodine and, wait, hang on. Okay, so they want to isolate solid iodine, but you're reacting potassium iodide and aqueous chlorine. So then, by the looks of it, my potassium iodide and my aqueous chlorine are going to be my reactants. So then how do I write that as formula so I can write a reaction out of it?
KiCl, Ki plus Cl.
Ki plus Cl. But here's where it gets a little tricky, because even though they're asking for solid iodine, you still have to remember that chlorine is one of your diatomic elements. So then I'm gonna write a little 2 in there, because it's really when they're in elemental state. Okay, so then from here, you know that you wanna isolate iodine, but then what other product are you gonna end up getting?
KCl, right?
We have KCl, and then how do I write my iodine as a formula?
Would it be?
It's a diatomic, so it would be I2.
I2, right? Okay. So far we've got that going on. Is this balanced? Can I work with this already?
No.
No.
No, right? So then what coefficient should I add to this equation to balance it out?
Do 1, 2. A 2.
2, 1, 2, 1.
2, 1, 2, 1. I'm just going to leave the other ones blank because it's redundant to write a 1. Okay. So now it's balanced. And before I even touch my grams, what are they asking me for in my question? If they're saying electrons transferred, what kind of problem is this going to be?
Redox.
Reaction, right? Redox has to do anything with electrons being transferred. So if this is going to be a redox reaction, what do I have to find about each one of these atoms?
The oxidation number.
Their oxidation numbers, right? So I'm gonna go ahead and get started with my Ki. So I have potassium and iodine. So I want to find the oxidation number for both of these. So then for this one, since we don't have any elements isolated, they're not by itself, the compound doesn't have a charge. So then for this one, I can just assign oxidation numbers based on their charge when you split them up. So then what are my oxidation numbers for potassium and iodine?
+1, -1.
+1, -1. Easy peasy for that one. Okay, now moving on to my chlorine. It's combining, self-combining compound because there's 2 of them. So then what's my oxidation number going to be for this one?
0.
Because it's just an elemental state and it doesn't have a charge. Okay, so now moving on to my other side, I'm starting off with potassium and I have chlorine. So what are my oxidation numbers for these?
+1, -1.
+1, -1. There you go. And now for my iodine?
0.
0.
Right? Okay, so now I have my oxidation number. So then now what can I determine from these?
Electrons transferred.
Yeah, so I can determine what was oxidized and what was reduced. So then I'm going to start off with my potassium. I started off with +1 and ended with +1. Did this one go through redox?
No.
No, right? So I'm not even going to worry about this one in my redox reaction. So then now I have iodine. I started off with -1 and I end up with 0.
The chlorine is reduced and the iodine is oxidized.
There we go. I like how we're just like, hurry up, Brittany. We just want to get this over with. Okay. So then we have reduced, oxidized. And then for those of you, maybe if you're still having trouble like telling the difference, one thing that I like to use with my students, I like to like have them draw a little number line. So at the middle, you have your 0, all your positive values on the right, all your negatives on the left. And then at the top, I usually draw 1 arrow going to the left, 1 going through the right, and then I just write redox at the top. So then if my value
Isn't that backwards though? Isn't chlorine reduced because it becomes more negative?
Yeah, mayhaps. Here, this is where we're going in. Maybe this will like help you change your answer. Here we go. Okay, so then if my value gets more negative, then it's reduced. If it gets more positive, it becomes oxidized. So then just kind of like try to place your oxidation numbers on a number line and then compare it to the one you get on your product side. And then just off of this number line, try to figure out whether it's reduced or oxidized. So then now that we have that in, does that change our minds about which one's oxidized, which one's reduced? I think someone mentioned that it's actually flipped, right? So I'm going to go ahead and rewrite these. Okay. So then in reality, since my iodine started negative and then moved to the right, it got oxidized. And my chlorine was the one that got reduced. Okay. So now onto the ugly part about redox reactions, and that's writing half reaction equations. So then if I'm going to start off with my iodine, okay, so on my reactant side, how many iodines total do I have on my left side?
2.
2, right? So I have 2 iodines, and with what oxidation number?
-1.
-1. So that's how I started it off. And then as my product, I ended up with how many iodines?
2.
And with an oxidation number of?
0.
Okay.
0.
So then now to determine how many were reacted, then you would multiply your coefficient times your oxidation number. So then 2 times -1.
-2.
-2. And then on my right side, 2 times 0.
0.
0. So then what's the difference between -2 and 0? How many electrons are at stake here?
2.
2, right? So for now, I'm gonna toss them up here and then now to decide on which side they're gonna go. So then now for this bit, try to remember your oil rig mnemonic. So then if my iodine is being oxidized, did I lose or gain these electrons?
You lost them.
I lost 2 electrons, right? So then the way I like to picture it is, okay, I'm starting off with these 2 iodines. And then once I go over to my right side, they split apart from my elements. And now they're broken up into 2 things. And that shows that I lost my electrons. So then because of that, I'm going to put my electrons on the right side. Hopefully that makes sense. Okay. And now let's work with our chlorine. So I started off with how many?
0.
With 2.
Oh, 2, yeah.
0.
0, and then it turned into how many?
2 with the charge of -1.
2 of -1. And also this kind of serves as a check that, you know, you do start with the same number of atoms and end with the same number, just to double check that your equation at the very top is balanced. Okay, so then same thing, multiply coefficient times oxidation number. So then for this one, you should have 0. For this one, -2. So then what's my difference between these two?
2
electrons, right? And then since my chlorine was reduced, and I look back at oil rig, were those lost or gained? Gained, right? So then since I gained these electrons, now I'm going to go ahead and put them on my, what's that? On my left, because since I'm gaining them, this guy right here is gaining these electrons to turn into this guy right here. So then for now, we've got our half reaction equations going on. So then we know how many electrons were transferred. So then right now, we're just gonna keep this number in mind, because obviously if you look at your answer choices, there isn't one that just says 2, right? There's obviously more to this question. Okay, so then now I'm just gonna make a quick little note on the side that I transferred 2 electrons. So again, that was just also kind of practice on how to write your half reactions. There we go, scribble. Okay. So then I know 2 electrons were transferred. And then now I can take into account my 25.38 grams of iodine. Let me do a different color just to make our board look pretty. Okay. So then we have 25.38 grams of solid iodine, which is I2, and we want to know how many electrons were transferred. So then if we're starting off with grams, what's our safest bet that we need to convert this number to?
Moles.
So moles, right? So then we're going to go ahead and do the usual, 1 mole of I2 at the top. And for my grams, don't forget that there's 2 molecules of these. So then what's my atomic mass going to be?
253.8.
253.8. Okay. So now from there, we can go ahead and convert to moles of I2, and that should give me what?
0.1.
0.1, right? 0.1 moles of iodine. Okay. And then from here, we're obviously not stopping at moles. So then what should we convert these moles to if we want kind of like something smaller? And also, it should be a big hint on your answer choices of what you're going to need to convert to.
To atoms.
Atoms, right? Because they're giving you numbers like times 10 to the 20 stuff. Okay, so then what do I convert? Like, what's my conversion factor for this?
1 mole on the bottom.
1 mole on the bottom. And how many molecules does that yield me?
6.22, 0.22, e to the 23rd.
Awesome. I love that you have this big number memorized. Okay, molecules of I2. So then after you convert this guy, how many molecules should you get?
6.02 times e to the 22nd.
6.02 times 10 to the 22nd, and that should be molecules of I2. Okay, so now we're at molecules, and now we can kind of figure out our electron transfers. So then from here, for 1 molecule of I2, how many electrons were transferred?
2.
2.
Right? So then now punch this in to your calculator, and what do you get?
(1.2 e to the 23rd.
Times 10 to the 23rd, and that was the electrons transferred. So then that should get you answer choice C for number 7. Do we have any questions on this one?
I'm kind of confused about the electrons transferred. So do we only count the electrons transferred if it was oxidized, or if it was reduced, or?
Well, technically, when there's an electron transfer and you write your half reaction equations, the amount of electrons that you lose in your oxidation number is the same amount that are gained in your reduction. So then this number should remain the same for both your oxidation and reduction. So then if they were to ask you a question like this on your exam, just use that number that they have in common on the electrons to convert from molecules to electron transfer.
Oh, okay.
And also, that's a way to double check your half reaction equations. If you like work them out and you realize that you don't get the same number of electrons, then that should give you like a clue that, okay, something must be off. Like maybe the way I balanced my equation, or the way that I wrote down, like somewhere down there, my oxidation number. So then that also serves as a double check. If you have the same number of electrons on both your reduction and your oxidation, then that should give you a good signal that you're on the right track.
Thank you.
Any other questions? Okay. If you don't have anything to add, then I'm going to go ahead and hand it over to Sophia, and moving on to number 8. Where did I leave it?
Okay, cool. Thank you, Brittany. Okay. So for number 8, can someone read it for me actually? Please.
A scientist isolated a compound in processed food which consists of 61.01% carbon, 15.81% nitrogen.
Okay, 61.01% carbon. Okay.
And then 15.81 nitrogen, 18.06 oxygen, and 5.12% hydrogen. That has a molar mass of 354.364 grams per mole.
I'm sorry, that's so ugly. Continue, it's fine.
Which of the following is the correct formula for the unknown compound?
Okay, so for these kinds of problems, we have to find the formula, right? So you have to, so if you sum all these up, guys, you're supposed to get 100%. So that being said, you are gonna take the percentages away of these. So how would you take the percentages away for carbon, for example?
Well, wouldn't you convert 61.01% to 61.01 grams, or?
Well, okay, yeah, we can do that. Okay, so when you have 100%, you have 100 grams, right? Okay, so how will you convert this into grams? You would have to divide by 100, right? So the way you do this, so yeah, for example, Evelyn wrote, so for carbon, it would be 0.6101, right? Okay, and then for nitrogen, what would it be, guys?
For all of them. So like, since all of them add up to 100 grams, then you can just keep it at 61.01 grams, 15.81 grams, because then at the end, they all add up to 100.
Yeah, okay. So you don't want me to do this then? Are you saying, is that what you're saying, Brittany?
Oh, however you choose, just as long as like the answer is fine.
Oh yeah, no, the answer will be, okay, so I take the percentages away, that's why. Is that okay? I don't know.
I get what Brittany is saying, 61.01 grams, right? That's how you would say it?
Yeah, that's usually how like I do it, but maybe you'll learn a new way to do it today with Sophia. So let's not try to like just stick to one process when there's a lot, you know?
Okay.
Okay, so I'm gonna do it my way real quick, and then like I'm pretty sure that it gave me the answer, but like, okay, so well, yeah, I take the percentages off, guys, and then so for nitrogen, what would it be?
0.1581.
Yeah, so 0.1581, and then for oxygen,
0.1806.
0.1806, and then for hydrogen,
0.512.
0.0512, right? Okay. Cool. Okay, and then what you do, guys, is that you have to divide these numbers over the mass for the mass of the element. So, for example, for carbon, what would you have to divide it over?
12.01.
12, right? Okay, so did someone say 12?
Yeah.
So it's 12.01, but I'm just going to leave it at 12. And then for nitrogen?
14.
14, okay. And then for oxygen?
16.
16. And then for hydrogen? Just one. Okay, so what do you get after dividing these guys?
You get the moles.
Yeah, exactly. So, and for example, when you divide for carbon, when you divide 0.6101 over 12, what does that give you?
5.07. Oh, sorry, because I did that the other way.
No, it's okay. So 0.6101 over 12. Did anyone get something else?
It's 0.0507.
Okay, 07. Okay, cool. And then for nitrogen, when you divide 0.1581 over 14, what does that give you?
0.0113.
Okay, perfect. And then what about oxygen, guys?
Same thing.
Same thing, right? Okay, cool. And then lastly for hydrogen, it's just over 1, so
0.051.
right? Okay, perfect. Okay, so now that you've divided this, you then have to divide by the smallest number, which in this case would be which one? What is the smallest number out of all of these guys?
0.0113.
Yeah, exactly. Okay, so it would be over 0.013. Same for all of them. Okay. Okay, fine. And then, so what do you get, guys? So for these, it's easy. It's just 1, right? And then what about these two?
4.5.
4.5, thank you. Okay, and 4.5 for this one as well? Approximately?
Yes.
Correct. Okay, so the thing is, guys, that 0.5, that's a lot, right? So you have to get the closest to like a whole number. So what you would do is that you would, how can I make these 4.5 like closer to like a whole number? What do I have to do to them?
Multiply by 2, so it would become 9.
Yes, thank you, Sophia. Okay, so yeah, so multiply by 2, so that's 9. And then I have to multiply all of them by 2, right? And then, so 2, 2, and 9. Okay, perfect. So now all of these are like my whole numbers, so I would get C9, N2O2, H9, right? Okay, so now let's find the molar mass of this, guys. So we said carbon has a mass of 12 times 9, and then plus nitrogen has a mass, we said, of 14 times 2, and then oxygen has a mass of 16 times 2, and hydrogen has a mass of 1 times 9, right? Okay, so what does this give you?
Wait, why are you doing that? Oh, 12.
Okay, so you have 9 carbons, 2 nitrogens, 2 oxygens. What's up?
Nothing.
Okay, you figured out why though? So
Yeah.
you have 9 carbons, so that's why it's 12 times 9, and then 2 nitrogens, 14 times 2, 2 oxygens, 16 times 2, and then we have 9 hydrogens, so 1 times 9. And then that should give you the molar mass of this compound we just figured out. So what did that give you guys?
Is it 177?
Yes, okay, so perfect. So 177. Okay, so look at your molar mass for the compound, or for the unknown compounds. So what can we do to this 177 to make it look more like this? So what do you see, guys?
You need to double everything.
You just have to double it, right? And if you double this, you have to double your formula as well. So when you double the 177, that gives you what?
C18, N4, O4, H18.
Yeah, so C18, N4, O4, H18, and then your molar mass, when you multiply 177 times 2, gives you 3 what, guys?
54.
354, right? Which is basically like the same, right? So do you see this in your answer choices?
Yeah, it's a B.
Yeah, exactly. It's letter B. Okay, perfect. Okay.
Trust the process. You see, Sophia had it down and you're all doubting her. Come on, you.
You're the one that.
Okay. What was that, Joe?
Nah, she was the one that suggested. She was the one telling you to do it the other way.
True, huh? Shame on me.
Okay. Any questions, guys? Okay.
Other way, sorry.
Yeah, go ahead, Nadia.
The other way, is it a little bit faster or it's the same thing?
So honestly, like I haven't tried it the other way. So, Brittany, do you want to try it the other way or?
No, we don't have to do it because I know it's taking time. I was just curious if it's a little bit faster.
Okay, it's because I don't know. Like this is how like I learned how to do these problems, but I don't know if Brittany knows another way. So.
Because I see where you guys were going with the route of just assume grams with the percentages. But in my opinion, I think just do it the way it feels more comfortable for you. Because you kind of force it, try to find the fastest way, but then if you're not 100% sure how to do it, and then like it completely messes up your answer. So then just try to do with whatever feels more comfortable, whether it's Sophia's way or the way you already knew, just as long as you get the right answer. But you're good. You're good.
Any other questions, guys?
Wait, I had a question. I got confused. Why did you say that we had to like double it to get the C18, NO, like all that?
Okay, so you know how, so this is a compound we get, right? I'm sorry, this is like so like getting messy. Wait, let me just like kind of delete. Okay, so when you double like the 4.5, you end up with like, remember you had a, oh, let me change the color. Okay, you had like, oh my god, I'm sorry. Wait, so you had, okay, cool. Okay, so you know how you ended up with the C and then you have a 9? So that's like the C9. And then N2, oxygen 2, and then finally hydrogen, you have 9, right? So when you find the molar mass for all of these, for like the C9, N2, O2, H9, it gives you 177. But then in the problem, the unknown compound has a mass of 354. So like the way you find that 354, like you can kind of see, so if you double 177, you get a 354. Does that make sense? But when you double this one, you also have to double your formula. So that's why like the 9 turns into the 18 and etc.
Okay, yeah, I got it. Thank you.
Yeah, no problem. Any other questions, guys?
So basically, if I didn't get to 354, would I triple the amount then?
Yeah, so for example, what if I would have said that instead of, I don't know, instead of having 354 for your unknown, you had 531 grams. So you would be like, okay, so what do I have to do with this 177? Like maybe triple it, right? So if you triple 177, it would give you in fact 531 grams. And if you tripled the 177, you would have to triple your formula as well. So this would be like C27, N6, O6, H1920, H27. Does that make sense?
Yes, got it.
Perfect. Okay. Any other questions, guys? You good? Okay, cool. So I'll leave Maddie to the next problem. Okay, I'm just gonna clear this. Okay.
Okay, so the next problem is which sample contains the most carbon atoms? This one, there's really no way to tell, like just from looking at the answer choices. You have to actually work them all out. So our first answer choice is going to be 10 grams of CH2O. So then if we're looking for atoms, what would be our next step here?
Convert to moles.
Yeah, convert to moles. Okay, so can anybody tell me the molar mass of this compound?
Be about 30, right? Yeah, 30.
Yeah, it's going to be about 30 grams of CH2O. And then we end up with our 1 mole. But obviously we're not looking for moles, so what's the next step in our fence here?
One mole on the bottom.
Yeah, we have our 1 mole. So then what would we put on top?
6.022
Yes, 6.022 times 10 to the 23. This is going to give us molecules of CH2O. So then what's the next part of our fence? Because it's not asking for molecules.
You'd have to get into the carbons, but
One molecule on the bottom equals 1 carbon atom.
Yes. We have 1 molecule and then 1 carbon atom. And then the way we can figure out how many atoms, just in case people don't know, you look at the subscript on your compound. So there's an imaginary 1 on our carbon right there. So it's 1 carbon atom. So if we plug this into our calculator, what do we get?
point out.
0.01 e to the 23rd.
Yeah.
You said 2.01?
Yeah.
Okay, 2.01 times 10 to the 23. And then it's going to be carbon atoms. Okay, so now we're going to go to our next answer choice, which is going to be, it gives us 7.92 grams. So we're just going to follow the same process as our first answer choice. So what's our molar mass of this compound? It's going to be C2H4O.
It's 48, well, like 48.04.
Okay, 48.04 grams. And then we have 1 mole on top. So then we're just going to follow the same process. We have our 1 mole on the bottom of our compound. And we have Avogadro's number on top, molecules, and then we have our 1 molecule on the bottom. How many carbon atoms do we have in our compounds?
2.
Yeah, we have 2 carbon atoms. So if we plug this into our calculator, what do we get?
The molecular mass of it is wrong. It's 44 grams.
It's 44 grams?
Yeah.
Okay. Okay. Did anybody get the carbon atoms in our second answer choice?
2.17 e to the 23rd.
Yeah, 2.17 times 10 to the 23 carbon atoms. Okay, so then what would be the molar mass of our third compound? It's C3H6O2.
.06.
Okay, and then we have Avogadro's number on top again for our molecules. So how many carbon atoms do we have?
3.
Yeah, we have 3. So if we plug this into our calculator, what do we get?
.95 times 10 to the 23rd.
Right. Okay, and then what's the molar mass of our last compound down here?
$88.
Yeah, we have 88 grams. And then we're going to use Avogadro's number again to find our molecules. And then we put our molecules on the bottom on our last block. So how many carbon atoms do we have?
4.
Yeah, we have 4. So what do we get when we plug this into our calculator?
2.12, the e to the 23rd.
Yes, exactly. So then which one gives us the most carbon atoms?
Option 2.
Yes, it's going to be option 2, and it's this one. I think your book tells you that D is the correct answer choice, but that's obviously a mistake since we did all our calculations, so this one is going to be your right answer. Does anybody have any questions on that problem?
Do we need to do like all the process for each answer, or can we just look for the carbon subscript? For example, on the in the A, we have 1.
Mm-hmm.
And for the D, we have 4. Can we just look just for that, or?
No, because like if it had just asked you about the compound and it didn't give you grams, like say this wasn't given to you, then yes, you could look at the subscripts and that would give you your answer, then this one would be right. But since it gives us a different number of grams for each one, you have to do the calculations to see which one is actually the most.
Oh, okay, thank you.
And also to add on to that, also take into consideration that your hydrogens and your oxygens are different for all of them. So that can change the weight of your molecule, or like the percent composition of your hydrogens and oxygens. So
we made a mistake in there.
Say that again?
We made a mistake. For the second option, it's not 44 grams. For the molecular weight, it's like 42.
Already. Well, for the sake of time, just make a little note to yourselves, and then if you want, you can go back and revise it and fix it. But right now, just so we can like move on and keep the flow going.
Okay.
Unless you want to like really quick, we can just change that 44 to 2 and then just multiply across and then give you like the new number for that answer choice. Actually, yeah, let me go ahead and do that because I know that most of us probably won't go back and check it.
I just did it. It's going to give you 2.27 times 10 to the 23rd. So this one is still going to be your answer.
She's fast. She's got you.
That was an ugly circle. Don't listen to my circle. There you go.
That was number 9, right?
Yeah.
Any other questions for Maddie before we move on to number 10? Real good? Give me a sign that you're live.
Yeah, we're good.
All right.
Okay.
It's definitely 44, but
Okay. 1 yes is good enough for me. All right. Alrighty, cool. You cleared up. I can't ever find like the little tool thingy. Okay.
It's a little trash can.
And it's because I think there we go. Like my faces of everyone is covering like the little text draw stamp thingy.
Oh.
We're all settled. Okay, we're settled. Alrighty, so now for number 10. There we go, pretty purple. This one, we have a scientist wants to find out the percent of nitrogen in nitrocellulose. And lucky for you, they give you the formula, which is C18H21, N11, and O28. Okay, and they want us to find out which of the following is the correct percent of nitrogen. So if they're asking percent of nitrogen, what are we going to be dealing with? Here's a hint. It starts with percent and ends with composition. Percent composition. Okay. Okay, so then, well, they give us our formula. So then when we want to find out the percentage of just one single atom, what's the first thing we want to do with the formula we're given?
I'll get the molecular weight.
Get the molecular mass, right? So then we'll go ahead and do that. I'm pretty sure you guys are experts at this by now. We have 18C times, insert molar mass right there, 21 hydrogens times molar mass right there, 11 nitrogens, molar mass right here, and 28 oxygens, molar mass right there. Okay. So then if you look at our periodic table, maybe you've been doing enough of these problems to already know these molar masses by heart. So what's my molar mass for carbon?
12.01.
12.01, and then for hydrogen?
1.008.
1.008, then nitrogen?
14.01.
0.01, and for oxygen?
15.99.
15.99. Okay, so then now individually after you multiply for each atom, for each element, how much do you get of each? Let's start off with carbon.
$216.18.
Say that again? It was a little muffled.
216.18.
There we go, 216.18. And then for my hydrogen?
21.168.
21.168. And for nitrogen?
154.11.
154.11. And oxygen?
447.72.
447.72. Okay, so now the obvious, we add everything up together. And what should our total molecular mass be?
$839.178.
839.178 grams per mole. Okay, so we have our total, but we're only going to focus on nitrogen. So now what do we want to do with this nitrogen guy?
Get the molecular weight of the nitrogen, so the 154.11 divided by the total molecular weight, and it'll give you the percentage.
By the total, right? Lucky for us, we already had this figured out, so we killed 2 birds with 1 stone. We divide by the total molecular mass. And then whatever you get, we want to multiply it times 100 so we can get a percentage. So then after you divide these 2 numbers, what do you get as your decimal number?
0.18364.
0.1836. We'll just cut off at 6, or nice percentage can have 2 decimal places. And then after you multiply times 100, or you can just move your decimal 2 times over, we're at 18.36%. And this should be our answer choice D. I know on the key it says like E or something, but obviously there isn't an E on this one, so that probably might just be a typo in the book. So then we're gonna go ahead and pick answer choice D. Okay. Do we have any questions on this one?
Nah.
Fair and simple,
We're
right?
gonna do this whole review.
Come again?
We're gonna do this whole review. The whole
Yeah, we're gonna go over, we're gonna try to go over the whole thing, but obviously you don't have to stay the whole thing. So if you have things to do, you can dip out whenever, and then if you have any further questions, you can just ask your respective peer leader. So yeah, don't feel obligated to stay through this entire thing. Okay.
If you guys have like specific questions that like everybody's kind of having trouble with, we can work on that too.
Yeah. Or if you want, you can flip through the review yourselves right now, and then stopping at number 18, because the ones after that, they deal with gases. And then if some of you have to leave, but you want to try to figure one of these out real quick before you have to go, you can pick one out and then we'll do that one. So you don't have to wait until your turn to figure it out.
So after 18, the review stops?
Yeah, after 18, because the rest of them deal with gases.
Oh, okay, perfect.
So we have 2 pages to go. We've already done 1 back and forth. But also know that this is going to be recorded, uploaded. So if you want to like go back and check later to see how to figure out one of the ones we're doing, you can just go back and watch the thing if you have to leave. Okay, if you don't have any questions, then we're gonna go ahead and move on to number 11. Sophia, if you're still there, because I don't see like the little screen.
Yeah, I'm still here.
All
Okay, so let me annotate. Okay, so for number 11, guys, it's telling you if 12.3 milliliters of a 0.200 molar solution of sulfuric acid was dropped on the floor, how many hydrogen ions need to be neutralized? Okay, so first, we would start by finding our moles of the sulfuric acid, guys. So remember that, anyone know the formula for molarity?
Over liters.
Moles over volume equals molarity.
Yes, thank you. So yeah, so moles over liters, moles over volume, right? Okay, so I'm giving my molarity in my liters. So I would just need to find my moles, right? So this would be what, guys? What would I have to multiply?
Molarity times liters.
Exactly. And what are my values that my problem is giving me?
0.0123 liters times 0.2 molar.
3 liters. Okay, so yeah, so we're giving 1.23 milliliters. So we have to multiply that by 1,000, right? I'm sorry, divide. Ah. Oh my God. Okay, there. So yeah, so you would have to divide by 1,000. And that would give you the 0.0133 liters, and then times 0.200 molar, right? And what does this give you, guys?
0.00246 moles.
0.246 moles of what is that?
Of sulfuric acid.
Exactly. And what is my formula for this?
H2SO4.
Yes, correct. Okay. So, and it's asking me how many hydrogen ions need to be neutralized, right? So I need to do dimension analysis for this. So you would start with your moles. So 0.00246 moles of H2SO4. And then, okay, so when you have 1 mole of H2SO4, or sulfuric acid, how many moles of hydrogen ions do you have? So look at your
2.
So right now, yeah, yes, exactly. So we have 2 moles of hydrogen ions. Okay. And then it's asking you, and then ions, what is that like? Would that be, that's like Avogadro's number, right? So when you have 1 mole of a hydrogen ion, how many ions is that?
6.022 times 10 to the 23rd.
Exactly. Okay, and then what does this give you guys? We have a typo in our answers, so you're not going to see the answer choice there. But what do you get when you do this?
2.96 e to the 21.
Yes. Oh, 2.96 times 10 to the 21, and then hydrogen ions. Okay, perfect. Okay, and this should be your answer. So ignore like the answers choice is giving there. They're wrong.
Why did you multiply by Avogadro's number just because it had an ion?
Yeah, because ions, they're, what are they called, Brittany? I forgot. Like I'm blanking on the word right now. But like when you're like dealing with atoms, protons, anything. How do you say that, Brittany?
Particle?
Yeah, any like any like molecule like particles, you have to convert to Avogadro's number. So since ions are in that like same like family or like range, I guess that's why you have to convert to Avogadro's number. Does that make sense?
Yes. Okay.
Like anything like molecular, I guess.
Yes. Yeah. Okay.
Okay, perfect. Any other questions, guys? Okay, cool. So, Maddie is gonna do number 12 with you guys.
Yeah.
So you're saying number 11, the workbook is a answer in the workbook is a mistake?
Yeah, so you know how in the answer choices you don't see the 2.96 times 10 to the 21? That's like this should be your answer.
Well, the answer in the workbook is 1.48 times 10 to the 21st. So
Yeah, that's what I'm saying, that we have a typo.
Okay.
Yeah. Okay. Okay, cool. Go ahead, Maddie.
Okay, so number 12 is asking, given the data below, what volume of this silver chlorate solution would contain 8 grams of silver? So if we have, it gives us, hold on. There. It gives us 8 grams of silver. And it gives you the molar mass of silver chlorate, which is going to be 294.7 grams per mole. And then it's also going to be 0.673 molar. It gives you the molarity. So what would be our first step here? If it's asking for volume, using the information it gave us, what's our first step?
Convert to moles.
Yeah, we're going to convert to moles. So we have our 8 grams of silver. So if we're going to use dimensional analysis, what's our next step? Or like what goes on the bottom? What's our molar mass of silver?
107.9.
Yeah. It's going to be 107.9. And then what's the next step in our fence?
It would be 1 mole of silver, right? Yeah, 1 mole of silver on the bottom, and then
We would have our 1 mole of silver chlorate on top because we have 1 mole of silver in our compound, and we can see that from our invisible 1 on our silver in our compound. Does that make sense?
Yes.
Oh, yeah, yeah.
Okay. So then what's the next step in our fence here?
You'd put like 1 mole of AgClO3 on the bottom and 274.7 grams on the top. 294.7, sorry.
Okay, so we have our 1 mole of silver chlorate. And then you said to use our molar mass?
Yeah. Right?
Yeah. So if it's asking for volume, like how are we supposed to get, how do we get volume if we're going to be using grams?
Take the
Because if we continue,
We'll get milliliters.
moles divided by the volume equals molarity. We have the molarity is what 0.673.
So the way I did it, oh, go ahead.
I think we just stop in 1 mole of silver chlorate. No?
But there's a 1-to-1 ratio. And we can just use the formula mass 1 volume, volume 1 equals mass 2 times volume 2. Can you use that formula too?
You would, like, that is a formula you can use for some of your problems. It's just not in this one because it doesn't give you like an initial molarity and a final molarity. It's not mass 1, it's molarity 1 and volume 1.
Oh, okay.
Molarity 2 and volume 2.
Okay.
So the way I did this one is I like completely disregarded our molar mass. And then instead of our 1 mole of silver chloride on the bottom, I used our molarity, which was 0.673. So we have 0.673 moles of silver chlorate, and then that's there are that many moles in 1 liter of silver chlorate. So then that gives us our volume. So if we plug this into our calculator, what do we get?
0.11.
Yeah, we got 0.11, and that actually is the right answer according to the book. Does anybody have any questions on that one?
Yes, I'm kind of confused on how you got 1 liter for the 0.673 m. I guess
because in our molarity right here, our units, instead of like if we have this big M, you always want to, it's always going to be moles over liters. So we have 0.673 moles for every 1. So then you just plug that in down here.
Oh, okay. Thank you.
Does anybody else have any questions on that one? Okay. I'm gonna go ahead and let Brittany take over for the next one.
Okay, I think Sophia's gonna do this one.
Okay.
Okay, so for this one, guys, it's kind of weird, but okay, so it's asking you which of the procedures below is the best procedure to make 500 milliliters of a 2 molar sulfuric acid solution. So, first of all, you need to see how many grams there are in 1 mole of sulfuric acid, right? So you would have to, okay. So when you have 1 mole of sulfuric acid, how many grams is that?
It's 98.1.
98.1? Perfect. So you have 98.1 grams of sulfuric acid. Okay, so now you can disregard you can disregard B and D, right? Because that's telling you 82.1, and that's like not sulfuric acid, that's sulfurous acid, right? So you're in between A or C. Okay, so look at the wording. So for A, it's telling you very carefully add together 98.1 grams of sulfuric acid and 500 milliliters of water. And for C, it's telling you very carefully dissolve 98.1 grams of sulfuric acid in 100 milliliters of H2O and dilute to 500 milliliters. So which one do you think it is, guys, and why? Like, just based off of, like, I know, like, in your lab, they teach you this. So, like, any, like, ideas, like, which one it is and why?
I think it's A because I'm pretty sure sulfuric acid is a liquid.
Can you repeat that? I didn't hear that. You broke up.
I'm pretty sure it's A because I think sulfuric acid is liquid.
Okay, so yeah, but I don't know if you've seen in your labs that when you're like doing an experiment, you have to add the acid to the water. So like you don't add them together, you add the acid to the water. So look at C and it says dissolve the the sulfuric acid into the H2O. So that's why like the wording is better for C. Does that make sense? Because when you're doing experiments, you put like acid into water, not the other way around or like both at the same time. Because then you'll make a mess. Does that make sense?
This has to do with titration, right?
Yeah, exactly.
Kind of.
Yeah, kind of. Exactly. Okay.
Yeah, so it's C.
Yeah, so it would be C, guys. Okay, perfect. Okay, and then for Brittany, do you want me to do 14 too?
It's a
Yeah, I did it. Like it's fine. I'll do it. Okay. Okay. So for 14, it's asking you which of the following occurs for the reaction below. And then like it gives you a bunch. Okay, so let's write the equation first. So it's giving you iron oxide solid plus aluminum, and then that yields aluminum oxide and iron, right? Oh, I forgot these, sorry. Okay, so first of all, let's check if the equation is balanced, guys. Is it balanced?
Yes.
Yes.
Perfect, okay. So let's find our oxidation numbers. So let's start with our iron oxide. So what would my oxidation number be for oxygen always, guys?
-2.
-2.
-2, right? Okay, and then how this times 3, so that's a -6. So what does my iron have to be? Because I have a 2 down here.
+3.
+3, right? Okay. Okay. So +3, and then like that makes sense, right? Times 2, that's a +6. So these would like cancel each other out. And then aluminum, what is it? What would be the oxidation number for that?
0.
0, right? Because it's just on its own. And then for aluminum oxide, for oxygen, what would it be, guys?
+3.
-3, +3, -2.
Yeah.
Yes, so +3, -2, right? And then again, it's the same thing. So -6, and then these times 2, a +6. Okay, and then finally your iron in the end?
0.
It's a 0 because it's on its own. Perfect. Okay, so like I know it's like super old, but like I always use this and it's like it always helps me. So I use like the oil rig. So oxidation involves loss and reduction involves gain of electrons, right? So iron, you have a +3 and it's going to a 0 oxidation number. So is it losing electrons or is it gaining electrons?
Gaining electrons.
Gaining, right? So and then if it's gaining, what's happening?
Then it's reducing.
Reducing, exactly. Reducing. Okay, perfect. Okay, and then what about oxygen, guys? What's happening with oxygen?
It is the same.
Just staying the same, right? Okay, and then aluminum. So I'm going from a 0 to a +3. So am I losing or am I gaining electrons?
Losing electrons.
Losing, right? I'm becoming more positive. Therefore, I am
Oxidizing.
oxidizing. Perfect. Okay, perfect. So now look at your answer choices. So it's telling me that iron, A is telling me iron is oxidized. So is that wrong or right?
Wrong.
That's wrong, right? Okay, and then it's telling you iron oxide is oxidized. That's also wrong, right? Because like you don't look at like whole compounds when it comes to oxidation numbers. And then what about C, guys?
It's correct.
It's true. Correct, right? So it's telling you aluminum is the reducing agent. And then, okay, so I know it's weird because you're like, okay, aluminum is oxidizing. Why is it the reducing agent? So yeah, so when it's oxidizing, that's going to be the reducing agent. And when it's reducing, that's going to be the oxidizing agent. So yeah, so C would be your correct answer. Okay, any questions?
No.
No? Okay, perfect. Okay. There you go.
Alrighty, I'm back to jump in. I'm ready now. Okay, so then number 15. I'm really noticing that someone wanted like specific ones done, and 15 was one of them. So then for these, they're asking, in the following examples, where does the oxidation number differ for the indicated element? So it's pretty much like, what are they asking here? Okay, so I see oxidation numbers, so then I'm gonna think module 6 right away. Where does it differ? So we probably have to find the one that's different for the indicated element. So whatever element they're talking about, we have to find which one changes oxidation numbers. So then we're gonna look at each one of our answer choices. So then starting off with, wait, this is number 15. There you go, because I get confused. Okay, so starting off with answer choice A, they want to know whether carbon, if its oxidation number changes in CO2- and in CH4. Okay, so then we're gonna find the oxidation number of carbon in each of these two compounds. So then let's go ahead and start off with the one for carbonate. We have carbon, we have oxygen in this compound. So then which of the two do we already know its oxidation number for? For sure. Like there's a rule to it.
Oxygen.
Hydrogen and oxygen.
-2.
-2, right? Okay, so then we're at -2. But then now to kind of put my puzzle together, figure out what I'm gonna get for carbon, what do I need to do to this -2? Do I only have one oxygen atom?
No, you have 3.
Yeah, 3, right? So I'm gonna multiply this oxidation number times the amount of oxygens I have. So then for oxygen, I should have a total of -6 for the entire 3 molecules of oxygen. So it's important to tell the difference that this -2 only corresponds to 1, and the -6 is for all 3 of them. Okay, so then now I'm at -6, and I noticed that this compound has an overall charge. So then once I sum up all my oxidation numbers, what do I want it to add up to? Say that again?
Oh, sorry. -2.
-2, right? Because when it has a charge, that's what you want your oxidation numbers to add up to. So then we're at -2 for the entire compound. So then what do I need to do to get from this -6 to this -2?
Add 4.
+4, right? And since I don't have multiple carbon atoms, I can just say that this +4 belongs to that one carbon atom. So then this +4 is my oxidation number for carbonate. Now let's check out the one for methane. Okay, so then I have carbon in this compound and I have hydrogen. So then what's my oxidation number for hydrogen in this compound? That's also one of your rules. Positive one, right? Because it's connected to a nonmetal, and when it's with a nonmetal, then it has to have a +1 charge. So then I have +1, but then how many of these hydrogen atoms do I have?
4.
4. So I'm going to go ahead and multiply, and this gives me +4. But does this entire compound have a charge?
No.
No, right? So then what do I want my oxidation numbers to add up to?
0.
0, right? So then what do I do to get from this +4? to this 0. Oh wait, hang on. I think something got a little funky here because I know this one's not going to be the answer. Hang on, here. Hang on, give me a quick little second. Okay, hang on. I think this one's gonna end up being a little typo, but let's just keep rolling either way to keep practicing our oxidation numbers. So then what do we do to get from this +4 to this 0?
-4.
-4, right? So then since I only have one carbon atom, I can just assign that number to the entire thing. -4. There we go. Unless I'm being mistaken and carbon is a metal, but I don't think so. Okay, we'll just leave it like that for now. Maybe that might have been like also a typo or something. Okay, anyway. So then it looks like this could be a potential answer anyway. So then we'll keep it in the bag for now. So we'll put a little question mark next to it because my oxidation number changes. Okay, so then now for the next answer choice B, we have to focus on the hydrogen in both H2SO4 and H2SO3. Okay, so in this one, kind of like to make our lives a little easier, instead of finding out like for every H and then every S, every 4, I'm just gonna go ahead and split this up into their respective ions. So then what's my charge for SO4 as an entity, like altogether?
-2.
-2, right? So then does my sulfuric acid have a charge?
No.
No, so then what do I want my oxidation numbers to add up to?
0.
0, right? So then now to figure out my hydrogen, what do I have to do to get from 0 to -2? Well, from -2 to 0, my bad. I worded that poorly.
Add 2.
Add 2. And then between how many hydrogen atoms do I have to split this oxidation number into?
2.
So I'm going to divide by 2, and my oxidation number for hydrogen should be a +1. Okay. Okay, so then now for my sulfuric acid, you can go ahead and do the same thing. So then what's my charge for SO3?
Negative?
-1?
-2.
-2. I think it should be the same, right?
Yeah. Big rule of 7, it doesn't matter the amount of oxygens, because it's like in that, the sulfur is in that same group. You know, they're both sulfurs, just keep the same charge to it. So yeah, it should also be -2. So then it's gonna be pretty much the same thing if I have the same H2 and this -2. Again, I can just, what does it take to get from 0? And that's gonna be +2, that +2 I divide by 2. So then my oxidation number for this one should also be a +1. So then since this one remained the same, I can just go ahead and not worry about it. I'm gonna exit out. Okay. So then now for my next answer choice, I have C, and they want me to find the oxidation numbers for fluorine in both HF, which is hydrofluoric acid, and into that very funky compound, which is Na2CO3F. There we go. Okay. So then for this, okay, first the easy one, HF, oxidation numbers for each of them. So then what's gonna be my oxidation number for fluorine?
-1.
-1, right? Because my hydrogen is +1, so then I know that my fluorine is -1. So then now for Na2PO3F, it's like, okay, where do I begin looking for here? don't try to like jump to your fluorine right away. Try to like see what you have first and then make sure that fluorine has like an established number. So then what we would do, I guess, is split these up kind of like into their ions. And then for my PO3, which is again rule of 7, what's my charge for PO3 altogether?
-3.
-3. Okay, and then let's look at my sodium, which is Na2. And then from here, what's my oxidation number for an Na ion? Or maybe all together.
That would be, I don't know, I think it would be 1 or 0.
Okay, so individually, because since it's in a compound, they're all bounded by ions. So the 0 is only when the Na2 is by itself.
It's a 1 then.
It has a charge of 1, so it would be 2 for Na2.
There we go. So individually, it's +1, but since there's 2 of them, altogether for the Na2 should be +2. Okay, so then now from here, if my entire thing does not have a compound, again, we want it to add up to 0. So then what's my missing value for fluorine?
Positive 1.
A positive 1, right? So then this one for fluorine should be +1. Okay, so then that one's also different. So then we're also going to keep it in the bag. And then lastly for C, for D, we have beryllium and the compounds beryllium sulfate and beryllium fluoride. Okay, so then for these, again, I guess you can kind of like split them up into ions. There you go. So you don't have to like find everything out individually. So then for my sulfate, what's my charge for sulfate?
-2.
-2. So then what's my oxidation number for beryllium?
+2.
+2. Okay, and then for beryllium fluoride, for my fluorines put together,
-2.
-2, because each one of them individually is -1. And then for your beryllium,
+2.
+2. So then for these, it looks like beryllium doesn't change. So then I'm not going to think about this. Now to choose like between A or C, I think on the answer key, it says C, but again, I think it might just be a typo again. So that's something for us to keep in mind to fix in our book, right? But at least out of this, like it'll teach you how to answer the question and to know how to approach it. So even if our key's a little off sometimes, at least now you know, okay, so I need to find oxidation numbers. I need to compare both of them, and then whichever one's different, then I'm going to put that as my answer.
I just want to jump in and say, I think A is the correct answer because according to the table for oxidation numbers that it gives you in your workbook, fluorine in a compound is always going to have an oxidation number of -1.
Yeah.
So I think that compound itself in answer choice C is a typo.
Yeah. And I think this guy right here was like a really funky compound to give out because you really wouldn't know where to start dissecting. So maybe if it would have been something easier like beryllium fluoride into this example, maybe that would have been easier to pick a better answer. So I think that's just a matter of the publishing in the book. But any questions on oxidation numbers whatsoever? We'll go ahead and go with this one. It's prettier. Okay. We only have about 3 questions left. So if you made it this far, thank you for being here and for giving us your time. But if you don't have any questions, then we'll go ahead and do number 16. That one looks like it should be a breeze. So who is it, Maddie?
Yeah.
Already.
So number 16, it's asking which would be considered the weak electrolyte. So basically a weak electrolyte is going to be anything that's not a strong electrolyte, I guess. So the way I like to remember, like, first of all, strong acids. I don't know if you guys were like know your 7 strong acids. But the way I like to remember it is the show CSI is on the network NBC. So then your 7 strong acids for your first one, it's going to be HCl, and then H2SO4, HI, and then HNO3, HBr, and then we have HClO4, or notice there are only 6 and I said there were 7 strong acids. You're also going to have HClO3. So these are going to be your 7 strong acids. And then for your strong bases, there's going to be, it's like a little letter B on your periodic table. So you have lithium, and then sodium, potassium, rubidium, cesium, barium, and strontium. So if you notice, these are all group 1 or group 2 metals on your periodic table, and it makes the letter B for base. And then for your strong bases, it's going to be any one of these metals paired with hydroxide. So this is going to be your hydroxide ion. So anything that's not one of these, one of your strong acids or your strong bases, is going to be a weak electrolyte. So going based off of this, which would be your weak electrolyte from your answer choices here?
C.
Yeah, I think I heard C. So H3PO4. This one's going to be your answer. This one's going to be your weak electrolyte because it doesn't dissociate completely into ions. So your strong electrolytes, whether it's a strong acid or a strong base, they're going to dissociate completely into their ions. And then weak electrolytes are only going to partially dissociate. Does anybody have any questions on that one? Nope. Okay.
All right. What is the group 1 and group 2 based on?
Your bases. These are going to be your strong bases.
You said that the bases pair, oh, sorry, with...
No, go ahead.
You said that the bases always pair something with OH, is that what you said?
Yeah, your strong bases are going to be any one of these metals that I drew right here. You can find them on your periodic table and they actually form the letter B. And your bases are always going to have the hydroxide ion, which is OH and a negative.
Okay, thank you.
Does anybody have any more questions on that?
I'm sorry, could you explain those strong acids again? It's because I stepped out.
Yeah. So the strong acids, so it's going to be like this little acronym, I guess. I don't know if you were here for that. It's CSI, like the show CSI is on the network NBC. There are only 7 strong acids, and this is a good way to remember it. So your first one's HCl, which is hydrochloric acid, and then you have sulfuric acid, which is H2SO4, hydroiodic acid, which is HI. Nitric acid is going to be HNO3, hydrobromic acid is HBr, and then you have chloric acid, which is HClO4, and then, oh no, that's perchloric acid, I'm sorry. HClO4 is perchloric acid, and then chloric acid is HClO3. So this is a good way to remember your strong acids.
Okay, thank you.
Does anybody have any more questions on this one? Okay. I'm going to pass it on to, I think, Sophia for number 17.
I think you're muted, Sophia.
Yeah, you're muted.
Yeah, thank you. Sorry, guys. Okay, so question number 17 is saying, A student combines a solution of rubidium bromide with an unknown solution and notes the formation of a precipitate in the mixture. Which of the following compounds could correspond to the unknown solution? Okay, so it's giving us ammonium hydroxide. Can someone tell me the formula for that? Ammonium hydroxide.
NH4OH.
Yes, okay, so NH4OH. And then it's aqueous, and then it's being combined with rubidium bromide. Can someone, and rubidium bromide, guys, would be Br, right? Okay, so what would this yield to? So it's a double displacement, right? So
Ammonium bromide and rubidium hydroxide.
yes, okay, so, okay, so ammonium bromide, so NH4 Br, and rubidium hydroxide, BH. Okay, so referring, if you don't have your solubility rules memorized, guys, you can refer back to page 119 on your workbook. And okay, so look at your table and tell me if these are soluble or insoluble. So for example, for my hydroxides, it's telling you that they're all insoluble except when they're paired with group 1 and ammonia or barium. So what is rubidium, guys? Is it a group 1? What is it?
Rubidium's group 1.
Group 1, right? So it would be so hydroxides are insoluble, but since it's paired with a group 1, this is going to be soluble, so aqueous. And then so look at your ammonia on your you see how ammonia is on your soluble table? So ammonia is soluble, right? So this is also going to be aqueous. So A is not going to be it, right? Okay. Cool. So now let's look at B. Okay. So B is telling me sodium sulfide with rubidium bromide, right? So what is my formula for sodium sulfide, guys?
NaSO4.
Na2S.
Is, what was that for?
Na2S.
Yes, so Na2S. Na2S, right? Because Na has one. Okay. Na2S. Okay. And then with rubidium bromide. Okay, so what would be my products, guys?
Sodium bromide and rubidium sulfur.
Okay, and is this balanced, guys? Just check your balancing real quick.
No.
All right, so you just like add a 2 here, and then a 2 here. And is it balanced now?
Yes.
Okay, cool. So thank you. Okay, so now that we balanced it, let's see if we have any precipitin in here. So looking at your table, guys, is sodium bromide aqueous or solid?
Aqueous.
Aqueous, right? Why?
Sodium's in group 1.
Yes, exactly. Sodium's in group 1, and group 1s are soluble, exactly. Okay, and then what about rubidium sulfide? Sulfides are insoluble, except when what?
With group 1.
Right? Okay, so it's going to be soluble then, so aqueous. Okay, so it's not B either. Okay. So now let's look at C, guys. So C is silver acetate. So any ideas on how would my formula for this be, guys?
AG something?
Yeah, so for sure AG, right?
COO.
Yeah. So acetate is C2H3O2, right? Or like, I know it's also like
CH3COO.
3COO, right?
Yeah.
But like, this is like a simpler way to write it, but it can be either. Okay. So, pair it with rubidium bromide, BR. Okay, let me know this is aqueous. Okay, so what would this form, guys? What would my product be?
Silver bromide and yeah.
Yeah, so silver bromide and rubidium acetate, right? So RB, perfect. Okay, so it's balanced. Okay, so look at your page 119, guys. So what does it say about, so what is bromide? Like, what is bromine, guys? Like, based off of your page 119, what like category does it fall into?
Halide.
Halides, right? Okay, and what does it say about halides? The halides are soluble except what?
Except with silver, mercury, or lead.
Exactly. So this is silver, right?
All right there.
So it's gonna be a solid. And then you know, well, it says about acetates. What does it say about that?
They're probably soluble except when, or insoluble except with group 1.
So for acetates, you look at your soluble table, and acetates are always soluble.
Okay.
Okay, so yeah. So for this question, it's asking you which of the following compounds could correspond to an unknown solution that forms a precipitate. So it would be C, guys. And then if you would do D, it would be like a similar scenario as A and B, like you would have aqueous products. Okay, any questions? No?
No.
Perfect. Okay, so I gotta step out, guys, but I'll leave you to Brittany and like we're doing a meeting job. So yeah, guys. And if you have any questions like for my students, you can always text me through GroupMe, okay?
Thank you.
Okay, thank you. Bye, Brittany. Bye, Maddie.
Hi, Sophia.
Yeah.
Alrighty, so we're at the very end. Last question, question 18. Hopefully you're all excited to almost get out of here. Okay. So then for this one, they're asking which of the following net ionic equation accurately denotes the formation of a precipitate when magnesium chloride reacts with lead to chlorate. So we don't have to like try out every single answer choice. We're just gonna start from scratch at the very beginning, and we're just gonna write our own ionic equations and then just match it to whatever answer choice fits best. And this also helps you practice, you know, writing your ionic equation. So then if they're telling me that magnesium chloride reacts with lead to chlorate, first thing that I'm gonna do ever when they only give you names, what am I gonna do with this information?
Write down the chemical formulas.
Write down chemical formulas, right? So then magnesium chloride, how do I write this as a formula?
MgCl.
MgCl.
2,
right? I like that you added that 2 at the end, because don't forget that magnesium has a charge of +2, chloride, well, chlorine has -1, so you need 2 chlorines to balance out your magnesium. Okay, so then we're reacting with lead to chlorate. So then what's going to be our second formula from here? How do I write lead to chlorate?
PbClO3.
ClO3.
2,
right? I like that someone just adds that little 2 at the end. Because yeah, don't forget that lead 2, the 2 that's in Roman numerals, that means that that's the charge of my lead. So then if my charge of lead is 2+ and the charge of my chlorate is -1, so then I need 2 chlorates to balance out that lead. So then don't forget your subscripts when you're writing down your formulas as well. Okay, so I'm gonna go ahead and rewrite that too. so we don't have it circled and confusing. Okay. So then from here, they don't tell us what we yield, but just remember double displacement. So then you want to connect these two, you want to connect these two. So then what are going to be my products for this reaction?
MgClO3 and PbCl2.
MgClO3 and PbCl2. Okay. So then now we have our reactants, we have our products. Are we balanced before we move on to anything? Does it look like we're balanced?
Yes.
Yes, right? So then we can go ahead and move on to writing our, well, actually not yet. I always miss the very important step. Before we can move on to writing our ionic equations, what do I need to determine for each of these compounds?
The state that they're in?
The state that they're in, right? So I need to determine whether they're soluble or insoluble. So let's go ahead and start off with MgCl2. You want to look at your chlorine. You'll almost always want to look at that last part of your compound. So then your chlorine is what kind of element?
Halide.
A halide, right? So are my halides soluble or insoluble?
Soluble.
They're soluble, and even though they have exceptions, Mg isn't one of them. So then what do I write here between parentheses?
Yes.
Aqueous.
Aqueous, yeah.
Aqueous, right? Don't forget that aqueous is your solubles, and your S's means solid for insoluble. Insoluble. Okay. So then now moving on to lead-2 chlorate. We're looking at my chlorate. Is my chlorate usually soluble or insoluble?
Usually soluble.
Say that again?
Soluble.
Soluble, right? And my PB doesn't look like it's any of the exceptions, so then what can I label this guy?
Aqueous.
Aqueous. Okay. So then now on my right side, I have magnesium chlorate. Soluble or insoluble?
Soluble.
Soluble. Yeah.
Soluble, so then I'm writing aqueous again. And now for my lead-2 chloride.
The solid insoluble.
Solid, therefore insoluble, right? Because my chlorine is soluble, but remember those hap elements that make it insoluble, and my PB is one of them. So then that one makes it a solid. Okay, so then now from here, now I can determine which ones I can split up into ions. So then which ones do I get to split up into ions? My aqueous or my solid?
Your aqueous.
Aqueous, right? So then we're going back to the beginning, starting with magnesium chloride. What two ions can I split that into?
Chloride and lead.
For this one? Not lead.
Magnesium and chloride and chlorine.
Magnesium and chloride.
Magnesium, but what's my charge for this? Don't forget your charges.
+2.
+2, because that's what makes it an ionic equation. And whenever something's just an ion by itself, go ahead and label it aqueous as well. And what other one?
2 chlorines with a -1 charge.
2 chlorines with the -1 charge. And again, since it's an ion, label it aqueous. So now moving on to my lead-2 chlorate. What two ions can I split this up into?
Lead +2.
Lead with the 2+, and it's aqueous. And what else?
Chlorate with -1.
Chlorate with -1. And how many chlorates do I have?
2.
There you go. Also aqueous because it's an ion. Okay, so now magnesium chlorate. What can I split this up into?
Magnesium +2.
Magnesium +2, aqueous, and what else?
2 chlorates -1.
2 chlorates -1, also aqueous. And then lastly, my solid, my precipitate, what do I do with this?
Nothing.
Nothing, right? I just rewrite it, leave it as is, because since it's in solid, it's insoluble, so it can't split up into ions to dissolve. Then I'm just gonna bring it down, label it solid again. Okay, so then I have this big long mumbo jumbo, and what do we call this equation?
Total ionic.
this is my total, right? Because this is the really long one with everything in it. So I'm going to label it total ionic. So now to bring it down to our net ionic, what do I want to do?
You can
Get rid of anything that's the same on both sides.
Anything that's the same on both sides. So then which ones can I look to cancel out?
Mg2 positive aqueous, 2ClO3 negative aqueous.
2ClO3, there we go. So then it looks like I'm going to be left with 2Cl minus, Pb2 plus, and PbCl2. So then I'm just going to bring it down and rewrite it how it is. So I have 2Cl minus aqueous plus Pb2 plus aqueous, and it's going to yield PbCl2 solid. Then again, this is my net ionic equation. And what answer choice does this one look like?
C.
The answer choice
E.
Oh,
C.
C, right? Okay. Thought I was hearing E. I was like, oh, that's scary. None of these is always scary. Okay, so then C, because that's where I have my lead 2, my 2Cl minus, and my lead 2 chloride. Leading to that answer. Okay. Do we have any questions on this one?
I don't think so.
No? Do we have any questions on anything from modules 4 through 6 before we all dip out? Any last minute concerns before your exam?
I just had a question just to make sure. You said for total ionic, to get to the net, you just cancel out whatever's like the same. It doesn't have to be like it doesn't have to literally cancel out. Like it doesn't have to be like 2 plus and then on the other side it has to be negative 2. If it's just the same, you cancel it out.
What do you mean?
So like, you know how you canceled out like Mg2 plus on both sides? Like I'm saying, like it does, like as long as it's the same, you cancel it out on both sides?
Yeah, so it has to be pretty much written exactly the same. It has to be the same element. It has to have the same charge. And then, well, usually if they're ions, they're already going to be in the same state of matter. But yeah, since everything's exactly the same, I'm just going to cancel it out.
Oh, okay. Okay, thank you.
Should also have the same coefficient.
Yeah, same coefficient. And if
Okay.
it looks like it's different for whatever reason, then maybe your balancing is off somewhere. So that's also a clue to go back in and recheck your balanced equation.
Okay, thank you.
Okay. Any other questions about anything?
So if we just study all of this, we should be fine for the exam.
Yeah, for the most part, this is the way that your exam questions are worded. So maybe it's like a good idea of how your exam might be. But obviously, if you feel like you want to practice more, so you can get the clue, so you can get like 100% the hang of the processes, then feel free to do so. But if just by doing this, you feel good to go, then you should be fine.
Thank you.
Okay. Any other things you'd like to add? Okay. If you don't have anything else, then I just want to say thank you guys for taking the time to be here. And hopefully we got to help you out a little bit. But of course, if you have any further questions after this, feel free to reach out to your peer leader. They're always there to help you out. And if that's everything you have for today, then you guys are good to go for the rest of you that are left.
Thank you.
Thank you.
Thank you. Goodbye.
Have a good one.
Thank you.
Thank you.
Like how everyone just unmutes to say thank you like throughout the entire session. Nice. They're polite. That's a good thing.
Yeah.
Alrighty, I'll just.
I think you can stop the recording now, Brittany.
Alrighty. How do I? Okay, I think I can stop sharing and I